This lecture is an introduction to public key cryptography, and in this first part I will focus on the basic constructions. So in this first lecture I will recall a little bit of history of cryptography, and I will also recall classical cryptography and some building blocks, so the block ciphers and hash functions. Then I will explain what is public key cryptography, and I will introduce some basic constructions, that is RSA encryption and RSA signatures, and Diffie-Hellman key exchange. Then in the next lecture, I will speak about security models. So how do we formalize the security of an encryption scheme or a signature scheme? And then I will explain how to encrypt and sign securely with RSA. So I will describe the OAP and the PSS schemes. Then I will explain what is a public key infrastructure, and so I will explain what are certificates, and also I will describe the SSL protocol. And then eventually I will provide a short introduction to Bitcoin and to the blockchain. So I start with a little bit of history. So a very simple encryption scheme is the substitution cipher, or the monoalphabetic cipher, in which we replace every letter of the text separately with another letter according to a fixed permutation. So, for example, we can decide that A becomes a C, B becomes a G, C becomes H, and so on. So we replace every letter separately in the text. So, for example, hello world becomes this encrypted message. So one could think that this is very secure because the number of possible keys is huge. So the number of possible keys is the number of permutations of the 26 letters of the alphabet, and this is factorial 26, which is approximately 2 to 88. So we could think that this provides 88 bits of security. And so doing exhaustive search will take a very long time. But actually this is not secure because in English, some letters are more frequent than others. So in English, the most frequent letter is the letter E, and also T and A. So we can make a frequency analysis in the text, and the most frequent letter in the ciphertext is likely to correspond to E. So we can substitute, and then we can continue with the less frequent letters. And in practice, for a long enough text, this is quite effective. And so we can quickly recover the permutation. And so this means that this technique is completely insecure. So let me now describe the one-time pad, which is actually a perfectly secure encryption scheme. So in the one-time pad, the plain text is a sequence of bits, and every bit is encrypted separately. So to encrypt a bit, we XOR it with the bit of the key to produce the ciphertext bit. So 0 XOR 0 is 0, 0 XOR 1 is 1, and 1 XOR 1 is 0. So the XOR is the same as the addition modulo 2. So for example, the first plain text bit, 0, is XORed with the first key bit, which is 1, so it gives 1 for the first bit of the ciphertext. And for the second bit, we get 1 plus 1, which is 0. So it's possible it's easy to see that the scheme is perfectly secure if the key is random and if the key is as long as the plain text. So this is easy to see because consider, for example, the first bit of the ciphertext. So here it is 1, and so this first ciphertext bit is 1 because the key is equal to 1 and the plain text bit is 0. But actually the key is random. So if we only know the ciphertext and not the key, we don't know what is the value of the key bit. And if this key bit had been equal to 0, then the plain text bit that we would recover would be equal to 1. And actually we cannot distinguish the two cases. So this means that we learn no information about the plain text bit. And so this means that the scheme is perfectly secure. But the scheme is not very practical because the key must be as long as the plain text. But still, it was used, for example, for the outline between Washington and Moscow during the Cold War, and the key material was delivered via the embassies of the two countries. The first encryption scheme that became widely used is the DS block cipher, which was developed in the 70s by IBM. So it was first published as a US standard in 1977, and then it quickly became a de facto worldwide standard. So the DS has now been superseded by the AES, the new standard, but still it remains in widespread use. So DS is a block cipher, so this means that for every key K, it is a permutation from the plain text to the ciphertext. So knowing the key K, we can encrypt a plain text block of 64 bits into a ciphertext block of 64 bits. And conversely, knowing the key K, we can go back and compute the algorithm in reverse order and recover the plain text M. And the length of the key is 56 bits, which is actually too short. So it was probably sufficient in the 70s when the scheme was developed, but now it is too short because we can now recover the key by a brute force attack. The DS block cipher is based on the Feistel scheme, which transforms a function f from n bits to n bits into a permutation p from 2n bits to 2n bits. So for DS, we have n equals 32. So as you can see on the right, there are 16 rounds of processing. So the IP and FP permutations are simply permutation of bits, and they have no cryptographic significance. So after the IP permutation, the plain text of 64 bits is split into two halves of 32 bits each, which are then processed according to the Feistel construction. So as we can see on the single round, we can see that this is indeed a permutation, because given the output A XOR f of B and B, we can recover the input of the round A and B by evaluating the function f. So, and to evaluate this function f, we need to know the key of the block cipher. And therefore, when we know the key of the block cipher, we can compute the 16 rounds in order from the plain text to the ciphertext. And conversely, when we know the key, we can go back from the ciphertext to the plain text by evaluating these f functions in reverse order. So what is inside these f functions? So the f functions takes as input 32 bits and outputs 32 bits. So the 32 bits of input are first expanded into 48 bits simply by duplicating some of the bits, and then we XOR with a subkey, which is so a subkey of the full key, which has 56 bits, and then the result, the 48 bits result, are split into 8 blocks of 6 bits each, which go as input of yes boxes. So every yes box takes as input 6 bits and outputs 4 bits. So this is the nonlinear part of the block cipher, which is, and every yes box is provided as a lookup table. And so this provides the nonlinearity which is required for a block cipher to be secure. And so after this, we obtain we obtain 8 blocks of 4 bits. So we obtain 32 bits, which are then processed into a permutation P, which is simply a permutation of the bits. So in summary, the f function takes as input 32 bits and outputs 32 bits using a subkey of 48 bits. And for every round, every of the 16 rounds, we use a different subkey. So with DS, we can encrypt a block of 64 bits, but how do we encrypt longer messages? And in cryptography, this is called a mode of operation of a block cipher, in which we use a block cipher in order to encrypt a long message. And the electronic codebook method is the simplest mode of operation, in which we divide the message into blocks, and each block is encrypted separately by the block cipher. But ECB is actually insecure, because if we have identical blocks in the plain text, then we get identical blocks in the ciphertext. So if there are some patterns in the plain text, then the attacker will observe the same patterns in the ciphertext. So some information is leaking from the ciphertext without knowing the key. Therefore, ECB, this mode of operation, is not recommended in practice. Whereas in the cipher block chaining, the CBC mode of operation, every block of plain text is XORed with the previous ciphertext block before encryption by the block cipher. And so this implies that each ciphertext blocks depends on all previous blocks of plain text that have been processed before. And then, even if we have two identical plain text blocks, the ciphertext blocks will be different with high probability. And so for the first block, we use a random initialization vector, and this ensures that even if we encrypt twice the same plain text message, then we don't get twice the same ciphertext. And this initialization vector is provided with the ciphertext. So this CBC mode of operation is well used in practice. But the problem with DS is that the key is too short. And when the DS was designed in the 70s, the key size of 56 bits was probably sufficient. But now, with increasing computational power, a brute force attack has become feasible. It is possible to do exhaustive search of the key. And this was actually demonstrated concretely in 1998, and a circuit of specialized hardware was able to break DES in only 2 days by exhaustive search. So we can say that now DES is insecure. And there are actually other attacks against DES, but they are less effective in practice. So there is the differential cryptanalysis, which was discovered by Biam and Shamir in 1990, and also the linear cryptanalysis developed by Matsui in 1993. So as we have seen, the 56-bit key size of DES is too short, and so to increase the key size, there is a simple technique, which is a simple construction, which is the triple DES. And so this is a simple method of increasing the key size of DES. We simply apply the DES block cipher 3 times to each data block. So the input and output size remain of 64 bits, but now the length of the key is 3 times 56, so 168 bits, because we use 3 independent keys. And triple DES is still widely used in practice, but it is now slowly disappearing because it is being replaced by the new AES standard, which is faster in software. So let me now explain why we must use triple DES instead of only double DES. Namely, we could try to use double DES with only 2 applications of the DES block cipher instead of 3. So we will have a first application with the left key L, and the second application with the right key R. But actually there is an attack against this construction. This is called a meet in the middle attack. And so assume that we know a pair of plaintext M and ciphertext C, and on the left, what we do is we start with the plaintext M, always the same plaintext M, and we compute all possible DES encryptions with all possible keys on the left. And on the right, we do the same. We start from the ciphertext C and we decrypt with DES with all possible DES decryptions, with all possible right keys. And now we know that for the true key, for the true value of the key, the 2 intermediate results must be the same. And so we are looking for a collision between the 2 lists, which would give us the key. But so actually this is a bit more complex because the block size of the DES is only 64 bits. So if we proceed like this, we will find plenty of collisions. And to get a unique collision, we simply have to encrypt 2 plain texts at a time instead of a single one. So eventually the complexity of the attack is 2 to 56. And so this shows that double DES does not provide more security than DES. And so that's why we have to use triple DES. So let me now briefly describe the AES block cipher. So this is the most widely used block cipher today. And so it is the new standard to replace the DES since 2001. And so now the input-output length is 128 bits instead of 64 bits for the DES. And the key length is to be chosen between 128, 192, and 256 bits. But the most widely used version is the one with 128 bits key. So let me explain briefly how it works. So the AES is based on the substitution permutation network. So this is different from the DS, which was based on the Feistel structure. And as we had seen in the Feistel construction, only half of the block gets modified in a given round. Whereas here, in a substitution permutation network, a given round modifies all the input bits. So the substitution permutation network is based on several rounds of S boxes and a linear layer. So the S boxes are the nonlinear part of the block cipher, and they are necessary for security because otherwise everything is linear and there is no security. And the S box should be a permutation. And so, as I said, unlike DES, all the input bits are modified in each round. So here in this picture, we have an example of SPN with 3 rounds. So for AES, more concretely, we have a sequence of 10 rounds. So this holds for the AES with 128-bit key. And so we start with the add run key, which is the XOR of the message with the first subkey, key 0, and which is derived from the key K. And then so we have these 10 rounds, and for every round we have first the sub bytes, which is the application of the S boxes, the nonlinear part, and then the shift rows and mixed columns, which are linear operations, and then the add run key to add another subkey. So this holds for the 9 first rounds, and then in round 10 it's the same, except that we don't have the mixed columns, and we end with the add run key with the last subkey. So let me now describe what is a hash function. So a hash function takes as input a message of arbitrary length and outputs a string of fixed length. So here are some examples of hash functions. The well-known SHA-1, which has 160 bits of outputs, and the SHA-2 and the new SHA-3 standards, which have 224 bits or 256 or 384 or 512 bits outputs. So in a hash function we take as input a message that can be very long, but we output a hash which has always the same bit size. So let me now explain what are the main properties that we expect from a hash function. So first, pre-image resistance. It means that the hash function is one way. We can, given the input x, we can easily compute h of x, the output y, but we cannot go back. That is, if we are given only y, we cannot go back. We don't know how to compute x efficiently. So the hash function should be one way. And moreover, the hash function should be also collision resistant. It means that it's difficult, it must be infeasible actually, to find two different messages x and x prime that give the same hash value. So to find a collision. So this is the most widely used property. And so to achieve this property, there is a minimal size of the output because of the birthday paradox attack. So given a hash function that outputs n bits, it is always possible. This is a generic attack, so an attack that works for any hash function, there is an attack that finds a collision, so that breaks the collision resistance in 2 to n over 2 operations. So this means that if we want to have a hash function that with lambda bits of security, we must have an output size of at least 2 lambda bits. So if we want to have at least 128 bits of security, the hash function must have an output of at least 256 bits. So what are the applications of hash functions? So a relatively straightforward application is to check the integrity of messages or files. That is, if we have a message M, we can compute the hash of M, and then if we can store this hash value, and then we can check that M, the message M, has not been modified simply by recomputing h of M and checking that we still get the same hash value. And in that case, this means that M has not been modified, otherwise we would have found a collision, and we assume that it is infeasible. So this means that in practice, if we want to protect the integrity of a message M, we don't have to store a copy of the long message M. We only have to store the short hash value. So for example, if you lend your hard drive to someone and you ask this person to not modify any file, you can check that the person has not modified any file by first, before lending the hard drive, you hash the contents of the full hard drive, and you store the short hash value. So the hash value is only 160 bits, for example, for SHA-1. And then when you get back your hard drive, you hash the hard drive again, and you check that you get the same hash value. And in that case, this means that your hard drive the content has not been modified. So another application of hash functions are commitment scheme. So assume that Alice wants to commit to a message M and to Bob, but without first revealing the message M. So what she does is she generates a random value R, and she computes the hash of H, the hash of R concatenated with M. And she gives only this hash value, not the message M, but only H, to Bob. And so in that case, Bob does not know the message M, because the hash function the hash function is assumed to be one way, so he cannot go back from the hash value to the message. And moreover, this is randomized. So even if he has some candidates for the message M, he cannot test them because he doesn't know the random R. And then later, Alice can decommit and reveal the message M and also R and to Bob, who can check that the hash of RM is indeed equal to H. So this means that he can check that the commitment of Alice to M. So when Alice must reveal the hash value, she cannot find another message M, because otherwise she would have found a collision. So this means that this is a commitment scheme. And also we can use hash function for proof of work, as in Bitcoin in the blockchain. So in the blockchain, we want to find a message M such that the hash value of M starts with k 0 bits. And so in principle, if the hash value of the message behaves like a random value, this is going to require 2 to k hash computations on average. So an exponential, the number of computations, the work to be performed is exponential in k, in the parameter k. But then when we want to verify that this work has been accomplished, we only have to compute a single hash value. We only have to recompute the hash of M. So this technique is used to create a blockchain, to protect the blockchain. So let me now explain the concept of public key cryptography. So public key cryptography was invented by Diffie and Hellman in 1976, and it was a revolution in the field. So now the difference is that each user has 2 keys instead of a single key. A public key, so that is public, that is used to encrypt, and a private key, which must remain private for the user, and which is used to decrypt. And of course, it should be hard to recover the private key from the public key. And the concept of public key cryptography is very powerful. It enables many things, so public key encryption, digital signatures, and many other protocols, for example, key exchange, identification, and so many other things. So now we have a key generation function, and in this concept, and this key generation function is applied by each user. So, for example, Alice applies this key generation function to generate her public key that she makes public and her private key that she keeps private. So why is the concept of public key cryptography so important? Because first it solves the key distribution issue. In symmetric crypto, in classical crypto, we have the following problem: how do we initially distribute the key to initiate a secure channel? So assume that Alice and Bob have never met before. For example, Bob is in Paris and Alice is in New York. So they have never met before. How can they? Is it possible for them to communicate securely? And what could think that this is actually impossible, because if Bob sends his key to Alice, then of course an eavesdropper is going to recover the key, and then he can decrypt all communication. Or Bob could make a phone call to Alice to tell her his key, but of course if the phone call is monitored, then there is no security. So this problem seems to be impossible to solve. But actually, thanks to the concept of public cryptography, it is actually possible for two persons, for example, Alice and Bob, who have never met before, to communicate securely and to establish a secure channel between the two of them. So how does it work? Bob is going to obtain the public key of Alice, so this should be easy because this key is public, and is going to use this public key to encrypt his message M, so he obtains the ciphertext, and then he can transmit this ciphertext over some insecure channel, for example, the internet. And then Alice, using her private key, but she's the only one to know, she uses her private key to decrypt the ciphertext and recover the message M. Now, even if there is an attacker on the channel, then the attacker gets to see the ciphertext, but he doesn't know the private key of Alice, so he cannot decrypt the ciphertext, and so Alice and Bob can now communicate securely without having met physically before. So we can make an analogy with the mailbox. So for example, assume that Bob wants to send a letter to Alice. First, he's going to obtain the public address of Alice, and then he puts his letter in the mailbox of Alice. So anybody can do this, but Alice is the only one who can open her mailbox and read the letter of Bob. So basically, in this mailbox, it's the same as in public key encryption. Anybody can put a letter in the mailbox of Alice, but only Alice can open a mailbox and read her letters. So how do we instantiate this concept? And the first concrete instantiation of public key encryption was described by Rivest, Shamir, and Adelman in 1977. So this is the RSA algorithm, which is still the most widely used public key encryption scheme, probably because it is quite simple to understand. So this RSA algorithm, as I will explain, implements a trapdoor one-way permutation. So I will explain what it means. So RSA can be used for many things, not only encryption, it can be also used for signature. I'm going to explain how. And so this RSA algorithm is basically used to secure the internet, because it is widely used in the SSL protocol, and also to secure email, and so it has many other applications. So as I said, RSA implements a trapdoor one-way permutation. So what does it mean? It means that if you start from X, it is easy to compute the function f, which happens to be a permutation. So it is easy. So anybody can easily compute f of x from x. But going in the other direction is hard. So going from f of x to x, back to x, is hard, and this is hard without knowing the trapdoor, because if you know some additional secret information, the trapdoor, then it becomes easy and you can recover x, and this is a permutation, so there is a unique x given f of x. And so this, of course, enables to obtain a public key encryption scheme, because then anybody can compute the encryption f of m of the message m. We apply the permutation m to obtain the ciphertext c, and then nobody can decrypt. Nobody can recover the message m, and only Alice, who knows this trapdoor, who knows the private key corresponding to our public key, can recover the message m thanks to the trapdoor. So how does it work? So I'm going to provide a quick description of RSA, and I will not go into the details. So for RSA, how do we generate the key? So we have to describe a key generation function that generates both the public key of Alice and the private key of Alice. And of course, Alice must run this key generation function by herself. She cannot delegate this to some other party, because in that case, this other party would learn the private key of Alice. So she must really generate the pair of public key and private key herself. So she's going to run this key generation function. So how does it work? What is inside this key generation function? So first, we generate two large primes, distinct primes, p and q, of the same bit size, k over 2, where k is a parameter. And now, so these primes p and q must be kept secret, and we compute the product of p and q, so n equals p times q, and n becomes the public modulus. So here I write in green what becomes public, and I write in red what must be kept private. And we also compute the Euler function of n, so phi of n, which is p minus 1 times q minus 1, which is also a secret information. So only n, the modulus n, p times q, becomes public. So then we generate a random integer e, which is co-prime with phi of n, so the GCD of e and phi of n is equal to 1. And then, using the extended Euclidean algorithm, we compute the unique integer d, so this will be called the private exponent, such that e times d is equal to 1 modulo phi of n. So e and d are modular inverses of each other modulo phi of n. And then, eventually, the public key is n, so the RSA modulus, n equals p times q, and also the public exponent e. So e is called the public exponent. And the private key is the private exponent d. So here we have explained how to generate the RSA key. The public key is n and e, and the private key is d. So let me now explain how to encrypt. So we will assume that we are given a message m. So we assume that the message m is between 0 and n minus 1, where n is the modulus. So we get the recipient of the message, the public key of the recipient of the message, so n and e. And to encrypt, it's quite simple. We simply compute m to the power of e modulo n. So the ciphertext becomes an integer modulo n, which is m to e modulo n. So as you can see, anybody can encrypt because we know the public modulus n and the public exponent e. And now to decrypt using the private key d, it's almost the same operation. We start from the ciphertext c and we raise c to the power of d modulo n, and we get the message m. So we can show that we really get back the message m. And now you see that only the owner of the private key can decrypt, because to decrypt we must know the private exponent d. So how do we encode the message? So as I said, we are going to view the message as an integer between 0 and n minus 1, but we can actually always interpret a bit string of bit length, the integer part of log 2 of n, so that the bit length of the bit string to be encrypted must be smaller than the bit length of the modulus n. And then we interpret this bit string as a number, modulo n. Okay, so I'm going to illustrate how RSA works using a Jupyter Notebook in Sage. So first we can define the bit size of our primes. So for example, 512. And then we can generate the prime p. So I use the random prime function. So here I get a random prime which is less than 2 to 512 to n. And let's print it. So we get p or prime p. We can generate also q using the same function. And now that we have p and q, we can compute the modulus n, which is p times q. And let's print it. So we get n, so this is this integer. Now we can define the public exponent e. So for example, we can take 2 to 16 plus 1. And now we must check that e is invertible modulo p minus 1 times q minus 1. So we compute the GCD of e and p minus 1 times q minus 1, and it should be equal to 1. Okay, it is 1, so we are good. We can now compute the private exponent d. So d is the modular inverse, so we use the inverse mod function of e modulo p minus 1 times q minus 1. So now we have computed the private exponent d. And now let's try to encrypt a message. So for example, for m, we take this integer 1, 2, 3, 4, 5, 7, 8, 9, and then we are going to encrypt to raise m to the power of e modulo n. So for this we use the power mod function, power mod of e modulo n to get the ciphertext. And let's print the ciphertext also. So the ciphertext is this integer. And now let's try to decrypt. So we perform the sum operation, power mod, but this time with the private exponent d. So power mod of d modulo n. And okay, we get the original message. So decryption works. So in practice, how do we implement RSA? So as we will see, we must compute with quite big integers. So to have a certain level of security, we must use an RSA modulus of 1024 bits and even larger sizes. So this means that in practice, we must perform operations with very large integers. And so the integers are much bigger than the registers of a CPU, of a 32-bit or 64-bit CPU. So this means that in software, we must implement a big integer library, which works with the 32-bit or 64-bit registers of a concrete processor, and then using this library, we can manipulate and make operations on arbitrarily long integers. So, for example, a very popular library is the GMP library. So that's for a software implementation, but we also have hardware implementations of computing with large integers. For example, on smart cards, because on smart cards there is a small processor, but sometimes the processor is not powerful enough to implement such a big integer library. And in that case, one can use a crypto processor, which is a dedicated hardware unit, which can perform these arithmetic operations, these multiplications, relatively quickly. And we have also some hardware accelerators for PC in case these exponentiations, these modular exponentiations must be performed repeatedly. So actually RSA is not very efficient, because encrypting a message with RSA is, for example, much slower than for AES, because we must perform arithmetic operations with very long, with very big modulo, very big number. So that's why in practice, if we want to encrypt a long message, it is better to encrypt only a symmetric key k. So it will be a short key, a short session key, that will be encrypted with RSA. And then the long message, which can be a few megabytes or a few gigabytes, will be encrypted with a block cipher. So for example, AES, and in that case, it will be much faster. So this is called hybrid encryption, because we are using both public key encryption and classical symmetric key encryption. And we are getting the best of both worlds, because we are getting the flexibility of public key encryption, and we are getting the speed of a classical block cipher. So how does it work? So if we start from a message M, we first generate this random key. So for every new message, we generate a random symmetric key. And then we encrypt the long message M using the block cipher, using, for example, AES. And this gives us, say, C2, the second part of the ciphertext. And C1 is the encryption with RSA, using the public key of Alice, of only this symmetric key K. So then the ciphertext has two parts, C1 and C2. And then to recover the message, first we start from C1 and we decrypt the ciphertext C1 using the private key to recover the ephemeral key K. And then using this key K, we can decrypt using AES to recover the long message M. So here, encryption will be relatively efficient because we only encrypt with RSA a small key and not the full message. So the question is, how secure is RSA? So as we can see, the security of RSA is based on the hardness of factoring. So given the product of P and Q, the RSA modulus n, it should be difficult to recover the prime factors P and Q. So we know that these prime factors are unique, but it should be hard computationally to recover these two prime factors. And actually, we don't know any efficient algorithm to do that. The best algorithms, they have sub-exponential complexity in the size of the modulus n. So this means that for a large enough modulus n, it becomes infeasible to recover the prime factorization and the prime factors P and Q. And the most recent factoring record in 2020 is the factorization of an 829-bit RSA modulus n. So this means that in practice, to have some margin of security, we should use at least a modulus of 1024 bits and even larger. But actually, factoring the modulus is only one possible line of attack. Of course, if you can factor easily, then you can break RSA. RSA has no security. But in practice, there are over attacks against RSA. So today I'm going to describe some of these attacks. So these attacks, they are the basic attacks against what we have seen, which is the textbook RSA encryption. So the simplest algorithm to encrypt with RSA. And there are also other attacks which are based on which apply when we use a small private or a small public exponent. And there is also the class of implementation attacks or side-channel attacks that are based on additional information. So by measuring, for example, the running time, we can obtain some information about the secret and recover the private key. And same with power attacks. By measuring the power consumption of the processor, we can derive some secret information and eventually recover the private key. And there are also fault attacks in which we can induce some faults on the algorithms. So let me describe some elementary attack against RSA encryption. So there is this dictionary attack, which is quite simple. So I assume that, for example, we have only two possible messages, M0 and M1. In that case, there are only two possible ciphertexts, C0, which is M02E modulo n, and C1, which is M12E modulo n. So this means that if you receive C0, since anybody can encrypt the message M0 and the messages M0 and M1. If you receive C0, this means that the corresponding plaintext is M0, and if you receive C1, this means that the corresponding plaintext is M1. So this is called a dictionary attack because we are making actually a dictionary of ciphertext, and in this dictionary we indicate the corresponding we can simply read the corresponding plaintext. So this shows actually that encryption must be probabilistic. We cannot use this simple textbook encryption. So this means that to a single message M, we must use some randomness to generate the ciphertext. So there should be a huge number, so exponentially many possible ciphertexts for every possible plain text. So in that case, a dictionary attack becomes infeasible because we cannot store this huge amount of possible ciphertext in a database or in a dictionary. So this prevents the dictionary attack. So for example, in the old PKCS1 version 1.5 standard for encryption, to encrypt a message M, first what we do is we concatenate to M some 0 bytes, then we concatenate some random string R, and we pad it with some constant, and this value is raised to the power of E modulo N. So here we see that encryption becomes probabilistic because to a given message M there corresponds many possible ciphertexts, as many as randoms R. But actually, for this specific standard, this is actually still insufficient because there was this Blaschen-Bacher attack, which appeared 20 years ago. So let me now explain the concept of digital signatures, and then I will explain how to sign with RSA. So what is a digital signature? It's a bit string that depends on both the message M and the public key of the user. So, and the property is the following: only Alice, who knows the private key, only the owner of the private key, can sign a message M using her private key to obtain the signature S. So the Alice is going to apply the signing algorithm using her private key to the message M to obtain the signature S. And then anybody can verify the signature of Alice on the message M, and using the public key of Alice. So using only public information, anybody, so for example Bob, can verify the correctness of the signature of Alice. So Bob is going to combine in a verification algorithm the public key of Alice, the message M which has been signed, and the signature S, and the verification algorithm outputs yes or no, and yes if the signature is valid, and no if the signature is invalid. So what does a digital signature provide? So a digital signature provides authenticity. So because only Alice can produce the signature of a message, and the signature which is going to be valid under her public key, because she's the only one who knows the corresponding private key. So nobody else can produce such a signature that is going to verify correctly under her public key. And a digital signature also provides integrity. So once a message has been signed, we cannot modify it because the signature is valid only for a specific message and not for any message. And these two properties, they provide the non-repudiation property. Alice cannot later claim that she did not sign the message because she's the only one who can sign a message under her public key. And once the message has been signed, nobody can modify it. So it's really Alice who signed this message. So how do we sign with RSA? So let me explain. So the key generation algorithm is exactly the same as before, as for public key as for RSA encryption. So we still have these two primes P and Q, which are multiplied to get the public modulus N. So we still have the public exponent E, and we have the private exponent D, such that D times E is congruent to 1 modulo phi of N. And so now to sign a message M, the signer is going to compute the signature, which is M to the power of D modulo N. So this is the same as decryption in RSA encryption. So we raise the message M to the power of D modulo N. And now we see that only the signer can sign the message because only the owner of the private key knows, so can sign. And then to verify the signature, we check that S to the power of E gives back the message M. And this must be true because actually raising, as we have seen with RSA encryption and decryption, raising to D and raising to E are inverse of operations. So if you, for example, when you raise to E, when you encrypt with RSA and then you later raise to D, you decrypt, you recover the original message. So here this is the same. If you first raise M to D and then you raise the signature S to E, you recover the original message M. So to verify the signature S, we check that when we raise S to E, we recover the message M. And this means that anybody can verify the correctness of the signature. And so no, actually, it is the same as for RSA encryption. There are many attacks against basic or textbook RSA signatures. What I have just described is textbook RSA, and we cannot use this simple signature scheme. So, for example, because there are many attacks. So, for example, the simplest attack is the existential forgery. So we can simply generate some arbitrary number R, and we raise it to E modulo n, and we say that M, the message M, is R to E. And of course, the message M will look random, but still, here we have obtained R, which is a valid signature of the message M. So, and we can do this without knowing the private key, by using only public operation. So here we are able to produce a pair of message and signature without knowing the private key, which is of course a bad property. And there is also a chosen message attack. So assume that we already know the signature of M1, so M1 to D, and we know the signature of M2 to D. We can simply multiply the two signatures, modulo n, and we obtain, by the homomorphic property of multiplication, we obtain M1 times M2 to D, which is actually the signature of M1 times M2. So this means that by combining two signatures, the signature of M1 and the signature of M2, we have obtained a third signature, M1 times M2. And we can do this without knowing the private key. We simply multiply two signatures modulo n, so using only public information. So, and again, it is a bad property, because simply by combining two signatures, we obtain a third signature without knowing the private key. So this is also a forgery. So to prevent from these attacks, the usual technique is to first use a hash function. And also the advantage of using a hash function is that we can then sign arbitrary long messages. So the message is first hashed. So given the message M, we apply some hash function, for example, SHA-1 to M, and then we can possibly pad it with some constant string, which is predetermined. And then this concatenation is raised to the power of D modulo n. We obtain the signature sigma. So this is what is used, for example, in the PKCS1 version 1.5 standard, which appeared almost 30 years ago. So to sign a message M, first we apply the SHA-1 hash function to M. Then we can concatenate some constant that depends on what is specific for SHA-1, and then some constant block. And the signature is then this mu of M to the power of D modulo n. So this prevents the previous attacks, because then we cannot obtain an existential forgery, because if we raise some number R to the power of E, it's not going to have this same structure, except with negligible probability. And also the chosen message attack is also prevented. So this is called the hash and sign paradigm. So first we hash the message, and then we apply the signature. We should not sign the message directly. So there are also other signature schemes which use different mathematics. So for example, the DSA, the digital signature algorithm, which is a standard which was proposed by NIST almost 30 years ago. So it is a variant of Schnorr and Elgamal signature schemes. And now the security is not based on RSA. It is not based on the hardness of factoring. It is based on the hardness of the discrete logarithm problem. So I will explain what it means. So to generate the public key, we compute G to the power of X modulo P. So G and P are public parameters. So they are known to everybody. And so the private key is X, and the public key is Y equals G to X modulo P. And then to sign a message M, we first generate a random a random k, and we compute g to the power of k modulo p, and then modulo q, where q is the divisor of p minus 1. And this gives us r. And then the second part of the signature is the inverse of k, k2 minus 1, times the hash of the message plus x times r, where x is the private key and r is the first part of the signature. And so the signature has these two integers, r and s. So this is the DSA, and there is also a variant of DSA, which is ECDSA, which is a variant for elliptic curves. So elliptic curves, the advantage of elliptic curves, this is an object that provides a group operation, and the advantage is that it gives us a much shorter public key than DSA. So roughly 160 bits instead of 1024 bits. So this is more efficient. And in particular, ECDSA is actually used in Bitcoin as a signature scheme to ensure that the funds can only be spent by the owner of the Bitcoin. The owner of the Bitcoin knows the private key, and so then it can only the owner of the Bitcoin can transfer his money. So let me now eventually describe the Diffie-Hellman key exchange protocol, which is actually historically the first public key protocol. So this Diffie-Hellman key exchange protocol enables two persons, Alice and Bob, to communicate securely and to establish a session key. And then they can use this session key using a classical symmetric key algorithm, for example, using AES. So assume that Alice and Bob have never met before. They are going to establish a secure link between them. So the algorithm is quite simple. We have the common, as previously, we have a common public parameters, G and P. So G is the generator of a subgroup of integers modulo P. And so Bob is going to generate some integer small b, and he computes, which he keeps private, and he computes G to the power of small b modulo P. And this gives him the big B that I write in green, and which becomes public, and that he sends to Alice. And Alice, similarly, she computes, she generates a small a, and she computes big A equals G to A modulo P. And she sends the big A to Bob. So they exchange the big A and the big B. And now Bob takes the big A that he has obtained from Alice, and he raises this value to the power of the small b that is private key. So this gives, when we replace the big A, this gives G to the power of small a to the power of b, and this is G to A times b modulo P. So this is the key that is computed by Bob. And similarly, Alice is going to do the same computation. She takes the big B that she received from Bob, and she raises it to the power of small a, her private key. And this gives us G to the small b to small a, and this is G to b times a. But this is the same as G to A times b. So this means that Alice and Bob are going to compute exactly the same session key. So Alice and Bob, they now share the same session key between them, and they can use this session key to communicate securely using, for example, a block cipher. And an attacker who obtains the big B and the big A cannot compute this session key because the attacker does not know the small a and the small b. So as we can see, the security of the Diffie-Hellman key exchange protocol is based on the hardness of what is called the discrete log problem, which is if we are given the big A in green, which is G to small a in red, the goal is to recover this small a, which is called actually the discrete log of the big A with respect to the generator G. And actually, it's the same as for factorization. We don't know any efficient algorithm to do this for a large enough prime P. That is, the algorithms, the best algorithms, they have sub-exponential complexity with respect to the bit size of P. This means that for a large enough prime P, at least 1000 bits, we cannot recover the discrete log efficiently. But the problem with this protocol is that there is actually no authentication. So it is secure against a purely passive attacker who can only obtain the big A and the big B, and then does not learn the secrets. But it is vulnerable to an active attacker who can modify the messages that are being exchanged by Alice and Bob. So, and what is called a man-in-the-middle attack. So let me explain. So as we have seen, Alice, so here this is the normal setting. So Alice and Bob are applying the Diffie-Hellman key exchange. So Bob sends his big B to Alice, and Alice sends her big A to Bob, and then they are able to derive the same session key. So assume that there is no an eavesdropper, so Eve, who is going to attack the key exchange. So now we assume that Eve is an active attacker. She can modify, she can intercept the messages that are exchanged between Alice and Bob. So Eve, she does the following. She receives the big B from Bob, and actually she modifies it. She instead of sending the big B to Alice, she generates a new B prime, small B prime, G2B prime, which is equal to big B prime. So she replaces the big B by the big B prime. But now she knows the value of the small B prime in red, because she generates this value by herself. And so she transmits, instead of transmitting the big B, she transmits the B prime to Alice. And similarly, when Alice sends the big A to Bob, Eve is going to modify this big A into big A prime, which is G to A prime for a red small A prime, which is generated by Eve. So now Bob, instead of computing the big A to the power of small b, since he has received this big A prime, is going to compute A prime to the power of small b, and this is G to A prime times b. And similarly, Alice is going to compute G to B prime times A. And as we can see, the eavesdropper is able to recover the session key, which is computed by Bob, because she can compute the big B to the power of small a prime, because she knows the small a prime. And similarly, she can also compute the key derived by Alice. She can compute the big A to the power of small b prime. So this gives exactly the same key. So actually, Bob thinks that he's communicating with Alice, but actually is communicating with Eve. And similarly, Alice thinks that she's talking to Bob, but actually she's communicating with Eve. So this is called a meet-in-the-middle attack. And this is possible because we assume that Eve can modify the communications between Alice and Bob. This is an active attack. So how can we prevent this kind of attack? By using some authentication. So this means that when Alice receives the big B from Bob, she must be convinced that it really comes from Bob. So this means that Bob is going to sign this big B using his private key. And similarly, Alice is going to authenticate her big A by applying her signature algorithm. And then the attacker cannot modify the big A and the big B because he cannot generate a valid signature. So, for example, there are also other protocols, for example, password-based authenticated key exchange in some IEEE standards. So, as a conclusion, what are the main lessons from the past? As we can see, cryptography is a permanent race between construction and attacks. So many schemes have been designed and many have been broken. But now this has changed with modern cryptography, because what we try to do is to come with proof of security. So first we try to have a concrete, a convincing definition of the security, a concrete convincing model of security. And then the goal is to construct and to design schemes for which the security can be rigorously justified. And another main lesson is that the security of a crypto system should only rely on the secrecy of the key and not the secrecy of the algorithm, because otherwise this is a single point of failure, and moreover, open algorithms enable open scrutiny.